Okay, so we are in week 7, and we'll continue with the linear algebra that we saw from last week. So starting off with this problem. So, so just wanted to make the notation clear. So P2 is basically the space of all polynomials of degree less than equal to 2. Likewise, P3. And so let's start off with the first question, which is we have this linear transformation, which is given by T of F is equal to 2 times F prime, F dash plus integration 0 to X 3 times Ft dt. Now, of course, uh, first of all, uh, why is this a linear map? Well, it is a linear map because the derivative operation is a linear map. So recall that a map is a linear map if it satisfies this property that if you have two vectors two vectors u and v, then then a linear map must satisfy T of cu plus v is equal to c times T of u plus T of v, where c is a constant. Okay. Now we're looking at the space of all polynomial functions, and the space of all polynomial functions is a finite dimensional. Uh, Here we're looking at um, so here the domain of this map T is P2 of R. So this is basically polynomials over R with the degree less than or equal to 2. And of course, it's a finite dimensional space. And now this is a linear map because this part is linear and this part is also linear. So when you see this integral 0 to x 3ft dt, this is also a linear map, as you can verify easily because it's the integral operation also um, acts linearly on the polynomials. So now the question is, what is the dimension of the null space and the range space of uh, T? Okay. Now the question is, so what is the null space? So null space is a space of the vectors such that they map to 0. So in this case, the null space would essentially constitute. Um, so let me write it down. NT is basically going to be polynomials Q in P2 of R such that 2 times Q dash plus integral 0 to X 3Q is equal to 0. Okay, so now is the question like, what is, so you immediately notice that the differentiation operation will reduce the degree by 1, whereas the integration will increase the degree by 1, right? So, so you have, so this, um, so let Q be a degree R, not R, let's use some other term, be a degree A polynomial. So A is somewhere between 2 and 0. So this term, which is integration 0 to x 3q, um, is a degree A plus 1 polynomial, right? Whereas the 2q prime is a degree, yeah, so the degree of this polynomial is um, is strictly less than or equal to A. So if A is positive, then it's less than A, whereas if A is 0, then it's 0. So it's less than or equal to A. So it's clear that if you have a degree A plus 1 polynomial and a polynomial whose degree is less than or equal to A, then if you add them up, it can only be equal to 0 if and only if Q is itself 0. So Q belongs to NT if and only if Q is equal to 0. Okay. So the dimension of the null space is in fact equal to 0. And the range of and the rank of this map T is basically the dimension of P2R, which is 3 in this case. So I hope this was clear. So it's a easy warm-up problem. All right. Now let's okay. Okay. So here you have a
Sir, excuse me. Can I ask one question, sir?
sorry, do you have a question?
Yeah, yeah.
Yeah, please.
Sir, what is the option for previous question, sir?
Uh, it's the last one, D.
Yeah, yeah. Okay,
Okay.
A or B, C or D?
It's
Okay,
D actually.
okay. Thank you, sir.
Okay. Okay. So, right. So let's look at this problem, the second one, where okay. So you have the set of these numbers Rn, where By starting off from the halfway point, the numbers are basically repeated. Okay. So essentially, so like let's just say, assume. So there are two cases. Let's say n is odd or n is even. So let's say first n is odd. So let's say n is of the form some 2m plus 1. So what this means is that you have these numbers uh, a1 to a2m plus 1. Right, such that your a1 to a m is just give me 1 second. Sorry, just give me 1 second. I'm trying to check if the question will I copied it correctly. Uh, from AI equals to a m plus 1. Yeah, I think I've copied the question correctly only. Right. So what is given to us is that AI is just equal to right. So I mean, just to be clear, what this notation is. So this notation is basically the floor notation. So it's the smallest integer, which is the largest integer, which is less than or equal to x. Okay, so it's kind of like uh, so. I think this is what it is meaning that let's say you have 3.14, then this is equal to 3. I think this is what it says. So so here the problem says that AI is equal to a uh, n plus 1 by 2. Okay. So here, let's say n is equal to 2m plus 1. So then that means that this is equal to a of m plus 1. And here you have a m plus 1 till a 2 m plus 1. Right. So here it means that all the coordinates till a m plus 1 is actually fixed. Okay. So now the question is, what is the dimension of W? So the dimension of W is essentially um, dim of W. So first of all, notice that this is actually a vector space. Okay. Like it's important that whenever we are given questions like what is the dimension of the space or the rank of a map, etc., it's like if it's not immediately obvious to you whether it is a vector space or not, you should basically verify the properties that yes, this is indeed a vector space. Whatever properties a vector space should have, should verify that. So here it's clear that it's a vector space. If you add if you add two vectors and if you multiply with the scalar, then this particular property would remain preserved. And so it would lie, so this closure properties would remain preserved. Uh, Therefore, it is a vector space. Now you can talk about the dimension of this vector space. And the dimension of this vector space um, is basically all the numbers that you have from, let's say, m plus 1 to 2m plus 1, which is equal to 2m plus 1. Sorry, which is equal to m plus 1. Okay. This m plus 1 is actually equal to n by 2 plus 1. Okay. And now we have done this for the odd case. For the even case where n is equal to 2m, I leave it to you to figure it out. It will also come out to be equal to uh, the floor of n by 2 plus 1. So this is the correct answer. Okay. So I hope this was clear. Let's move on. Okay. So it's given that okay, I mean, here there's a slight misprint in the problem, obviously. So H is a 2n cross 2n matrix where all the entries are equal to 1. And here it says H only. It should not say H. It should say I or I2n to be more precisely, which is the identity matrix of order 2n. Then the sum of the determinant and the trace of H minus I. Okay, so let's so it says det of H minus I plus trace of H minus. Okay. Um, um, just give me 1 second. I want to check if this problem is correct. Just give me 1 second. Sorry. Someone asked, please explain assignment 5 problems. We are in assignment 7 right now. Uh,
Sir, excuse me.
yeah,
But so
please.
But so many questions are wrong in the assignment, sir. That's why we want the answers for those questions.
Oh, I mean, I do not have access um to the questions of assignment 5. I mean,
Okay. So,
I'm
so where we
yeah.
get those answers for those questions? Where we get those answers for the questions?
You should be able to see the solution, no? The solution should be out, right? I don't know if the solutions are already out. Um, the
Sir,
solution should be out. Yes, no? Hello, can you hear me?
law. Ah, yeah, yeah. Sir. One second. Sorry, I'm sorry. Sir, for this answer is D, sir. 1 minus 2n for this problem.
Yeah, yeah. The answer is 1 minus 2, and you can prove this using induction, basically.
Okay.
That's how you can prove this. Yeah.
Okay.
Solutions are not visible, sir.
For which assignment?
For fifth assignment, sir.
Fifth
Assignment
assignment.
5. Yes, sir.
Okay. What is the date of what is the due date of that assignment?
Yesterday, sir. Uh, Wednesday. Last Wednesday. Means
Last.
fourth,
Oh, last.
fourth.
Ah, okay. Okay. It should be out uh in fairly soon. If you're not able to see, I don't prepare the solutions to the problems. The professor does it. So if you are not able to follow the solution, so if you think that there is still a mismatch between the solution, so it might be that you are wrong and the solution is something can happen. So just check uh, whether you're able to follow the solution, um, and whatever is there in the problem assignment. And if you're not able to follow the solution, if the solution doesn't seem to be correct and so on, then just let me know next week. Then I'll try to contact
Okay.
NPTEL on this problem.
Okay.
Okay.
Last previous 2 assignments, sir. Please once go
Previ-
through it.
Previous two means week 6 and week
Week,
5.
yeah, yeah. Yes, sir.
Week 5 and 6, sir.
Okay. Let's start off with week 5 first. Let the solutions of week 5 come out.
Okay.
Then you can and if you're still not able to follow them, just see, like, then just pinpoint me saying that, okay, this is the problem and this is the solution. uh, then uh, uh, then I can send them a message, basically.
Okay.
Okay, sir. Thank you.
Yeah. Right. So this problem you can just proceed by induction over here. So the trace part is 0 over here.
Law.
Hello. Yeah. Are you saying something? Right. So the trace part here is going to be equal to 0. Right. And when it comes to the determinant part, which is so the determinant will have the diagonals all equal to 0, and the rest all the elements will be equal to 1. You can proceed by induction on n, basically. So Okay, there might be other ways also where you can try to reduce this matrix into a row echelon form. That is, you take the matrix H minus I and reduce this into a row echelon form. Yeah, but I think the easiest the easiest way to do this is to just proceed by induction. Like take n to be like a small dimension, maybe like 2 or 3. Yeah, maybe like 2 or 4 maybe, and then you can proceed by induction on n basically. Okay. Okay. So here, T is given to be a map from R3 to R3, and you essentially they have given T how it acts on the basis vectors. So if it acts on if it is given to you how T acts on the basis vectors, you can compute the matrix corresponding to T. So the matrix corresponding to T is basically this. So you write T, let's say this is your basis. So then T with respect to this basis V is basically equal to TV1, TV2, TV3. So these are going to be the columns of this matrix. But you have to essentially write down the coordinates. So when you fix a basis, let's say V1, V2, V3 is a basis, uh, then you every vector now has a coordinate with respect to this basis, right? So that means that when you have this vector V1 plus V2, yeah, what is the question? Hello, what is the question? Problem 7 of assignment 4. Let me finish today's class. Let me finish the problems of today. Then let's wait around till the end of the session and then I can look at it. Right now, I can't go back and forth between previous assignments and the current problem set. Okay, so V1 plus V2 has a coordinate, and this coordinate is basically 1, 1, 0. Okay, so it's so if you had a vector which looked like alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3, then its coordinates would be equal to alpha 1, alpha 2, alpha 3. Okay, so the coordinate here is 1, 1, 0. Similarly, you have the coordinates for V2 and the coordinates for V3. So so when you write down this matrix T with respect to this basis B, so V1 goes to V1 plus V2, which is 1, 1, 0. V2 goes to V2 plus V3, which is 0, 1, 1. And V3 goes to V3 plus V1, which is 1, 0, 1. And now, of course, you are free to choose um, um, and now you can decide if the matrix is 1, 1 or not. If the matrix is 1, 1, that means in this case, because T is a map from R3 to R3. So essentially that would mean that the rank of T is equal to 3, which means that T must be, the determinant of T must be equal to, must not be equal to 0. If T were to be not 1, 1. So let me just write it over here. Uh, so T not 1, 1 in this case implies that determinant of T is equal to 0. So let's compute the determinant of T. So that's equal to 1 minus um, 1 minus 0 minus 0 minus 1, which is not equal to 0. So T is actually 1. Okay. So now you have to check the options. Um, so let's say you want to check what is T of V1 minus V3. To check what is T of V1 minus V3, it suffices to uh, uh, like you have this matrix which is 1, 0, 1, 1, 1, 0, and 0, 1, 1. If you were to take the, if you were to subtract the third column from the first column, so if you did C1 is equal to C1 minus C3, then that would basically give you the coordinates for T of V1 minus V3. Okay. So let's say, so let's do this operation on this matrix. If you do this operation, you get um, 0, 1 minus 0, 1, 0, minus 1, minus 1. Get 0, 1, 1, 1, 0, 1. Which is, if you now read this column, then in coordinates, this column is equal to V2 minus V3. So B is the correct answer. Similarly, you can check C and D and verify if they're correct or not. Okay. To check, for instance, if this option is correct or not, what you can do is you can take you can perform this column operation. You can do C1 is equal to C1 plus 2 times C2 plus C3. Right. Alternatively, what you can do is that if you want to, let's say, compute this thing, assignment 5 is what you're saying, right? Okay, have you checked the given solutions of assignment 5? You have to wait while um till
Sir,
the
excuse me, solutions are not posted anywhere, sir.
oh, solutions are not posted.
Yes, even from
Okay.
first assignment to still sixth assignment. We didn't
Okay.
get any solutions.
Okay. Just give me 1 second. I can't. I'm not able to find. Wait, you have mailed me. I can't see. Where have you mailed me? When have you mailed me? I don't see any email from you. Um, I mean, you have emailed the professor. I am not the professor. Yeah, I've shared my email ID. Wait, I'm not able to find access to the course myself. Why is this happening? Not go to the course. Excuse me. Can anyone, if you share the link to the assignment page for any of the assignments, let's say assignment 5 or assignment 6, whatever. Can you share the link to that page? I can't find it myself. Hello, can anyone share the link to that page? Can you? Oh. Okay, I don't have access to the um okay, I guess I don't have access to just give me 1 second. I'm trying to see if I can get access. Ah, okay. Now I've got access. In week 5. Okay. Just send me an email with the numbers of the problems that you find have incorrect answers. Okay. Um, I'm going to forward that email to NPTEL because the format of the assignment seems to be different from the format that I am kind of following. I'm following a previous year's format to the assignments. Uh, okay. So, okay. I think we should proceed for with today's assignments, today's problem set. Just give me 1 second. I'm trying to bring up a problem. Uh, I'll be back in like 1 minute. Attend the call.
हेलो सर बताइए
Okay. So before we proceed, let's quickly look at one concept. So we have talked about representing matrices, representing linear maps in terms of a fixed basis. Uh, so if there is a map from two vector spaces, let's say Rn to Rm, then for a given choice of basis, let's say if B and B prime are basis for Rn and Rm, then we know how we can represent the matrix uh, which corresponds to this linear map with for the fixed choice of basis. Now, of course, we can ask what happens if we change the basis, right? Um, so let's say um, let's say you have two bases, let's say B1 and B2 for Rn, and let's say you have a basis B1 prime and B2 prime for Rn. So if I know the matrix of T with respect to B1 and B1 prime, I can ask what is the matrix of T with respect to B2 and B2 prime. Okay. So in order to do that, um, so let's say you make use of a coordinate change relation. So let's say V is a vector in Rn, and let's say you have a specific coordinate set of coordinates for V. So you can write the coordinates for V as V with respect to your basis. Let's say you write B1. Okay. So this is basically the coordinates of V. Now, if you the same vector V will have some other uh, representation in a different coordinate system. Let's say B1 prime. Sorry. Yeah. Let's say in a different coordinate system, which is B2. It will have a different set of coordinates. Um, so there is a relation which relates how the coordinates in over one basis relates to the coordinates over another basis, right? So let's say you can write this V of with respect to B1 as equal to um, some matrix P. Right. So let's say you can write this the coordinates over B1 as equal to P times some the coordinates over B2. Right. Similarly, let and this P is actually independent of the choice of V. So let me just write it down. P is the coordinate change matrix. This holds for all V. Okay, and how do you determine what this P is? Well, um, so you have some set of vectors in B1. So let's say you write um, these vectors in B1 as equal to some uh, I'm using superscript notation here as some alpha n1, and let's say you write this b2 as equal to, actually that's not the appropriate notation. Let me just write it as alpha 1 to alpha n and put this over here. And here, let's say you have another basis, which is alpha 1 to alpha n. This is a different basis, let's say. Okay, so in order to determine what this basis is, um, let's say you write this, um, let's say you write these vectors. So what you can do is you can fix a standard basis. So let E1, E2 up to En be the standard basis. So standard basis means that it's uh, means that it's actually one for right. Let me just write it down. So that means that EI is basically equal to 0 at all but the ith position, where it's equal to 1 and it's 0 again. Another way of writing it down is this. This is basically equal to del ij. This is the Kronecker delta. Anyway, so in order to determine what this matrix P is going to be, you can represent the vectors alpha 1 to alpha n with a superscript 1 with respect to this basis E1 to En, and same for the vectors alpha 1 to alpha n, again with respect to this E1 to En. So let's say you write this. So let's say you write this matrix as something like this: alpha 2, 1, alpha 2, n times P. Okay. So when you are given two bases of of the space Rn in this case, the two bases of the space Rn are going to be related via a matrix of this particular kind. Okay. So if you sort of write this if you call this matrix as alpha 1, and if you call this matrix as alpha 2, there is going to be a relation of this form: alpha 1 is equal to alpha 2 times P. Okay. Now, if you have, if you give me any vector V, if you give me any vector V, with respect to this particular basis, whose coordinates are basically with respect to this particular basis. So then if you write alpha 1 dot V, then that is equal to alpha 2 times P times V. So this same vector that you have, so let's say, actually I should write over here like this, uh, here, here. So if you had a vector V whose coordinates with respect to V1 was basically this, then for the same vector, its coordinates with respect to uh, to B2 are related by this formula. That is V of V1 is equal to V of just give me 1 second. Check what I'm doing is correct. Right. So what you get over here is that the vector representation of V with respect to the basis B2 is basically equal to P times the representation of this vector V with respect to B1. Right. So essentially you just multiplied this thing. So you call this PV with respect to basis B1 as equal to V with respect to basis B2. Okay. Um, okay. So now let's say you have a linear map from Rn to Rm. Okay, and you have some vector x in Rn. Okay, and you have computed T of let's say Tx is what you want to compute, and let's say you have computed a basis T. Let's say you've computed a matrix corresponding to T, and in coordinates it comes out to be equal to, let's say, this matrix T multiplied with x. With respect to, let's say, V1. So say, let us write it in this way, say Tx of V1 prime, Tx of V1 prime is equal to, let's say, T times x on V1. Okay. So this is equal to T times x. Like when you write this thing in this particular format, you are now just dealing with matrices and coordinate vectors. Okay, you no longer have the abstract formalism of a vector. Okay, you are now just dealing with matrices. So this is going to be an M cross N matrix. So let me just write it down. So this this T is basically an N cross M matrix. It's an M cross N matrix. Well, wait 1 second. Yeah, it's an M cross N matrix. Okay. This is going to be a column vector of length n, and this is going to be a column vector of length n. All right. So this x times b1, you can write it down as equal to if we use this relation now, then this is equal to P inverse times x times b2. This is Tx of b1 prime. But now let's say you have a relation between b1 prime and b2 prime. So let's say you can write this guy as equal to in a similar way. Let's say you can write it down as equal to Q inverse of Tx of b2 prime is equal to T inverse times x with respect to b2. Okay. So what you get is that Tx with respect to b2 prime is equal to Q times T P inverse x with respect to b2. So it turns out that the matrix representation that you get with respect to the choice of basis b2 and b2 prime. So let me just write it down over here. So if you, so your T now with respect to the basis b2 comma sorry b1. Wait one second. So your matrix T with respect to b2 comma b2 prime is given by Q times T, which is the matrix representation corresponding to b1 comma b1 prime P inverse. Okay. So this is the basically going to be the relation between the two different matrix representations that you get, where in order to determine these matrices Q and P, what you need to do is you need to take one set of basis vectors. So here, let's say this B1 was, let's say this is B1 with one set of coordinate vectors, and let's say this is P2, the other set of coordinate vectors. And if you write this in this way, then you'll basically end up getting is that this P guy is going to be equal to alpha 2 inverse of alpha 1. This is what this P is going to turn out to be equal. Okay. Right. So let me just bring up one problem. I'm not going to finish the computation. In many cases, the computation is going to be much easier than this. So let me just bring out one problem. Okay. Right. So what is given to us is two coordinate systems B and B prime, and we know the matrix corresponding to T with respect to B and B prime. Now the question is, what is this T with respect to B prime comma B? Okay. So right. So this is a case where you basically need to apply this result over here. So let me just indicate what what the matrices Q and P are going to be over here. So you're first going from B to B prime. Um, right. So I mean, let me just abuse notation a little bit, and let me just denote B as this matrix 1 0 0 0 1 0 0 0 1. Okay. And again, let me just write B prime also in a similar way. Right? So I'm just abusing notation a little bit over here. I'm indicating the basis and the matrix corresponding to it in using the same notation. So B1 prime is equal to 1 1 0 0 1 1 and 1 0 1. Okay. So now you can write this B as equal to uh, essentially we're using the same idea from here. You can write this B as equal to B prime times P. Okay. So your P is basically equal to B prime inverse times B. Okay, where B is just the identity matrix, so it's just equal to uh, B prime inverse. Okay. So that is going to be your P, or your P inverse is just going to be equal to uh, is just going to be equal to B prime itself. Okay. Now, next is determining the matrix Q. So for determining the matrix Q, you're basically going from B prime to B. Okay. So you write again this B prime as equal to B times Q. Okay. So your Q is just equal to B prime because B is just the identity matrix. Okay. Right. So this is how you're supposed to determine the matrices P and Q, and then you can uh, carry out this computation. Okay. Okay. So I hope this is clear. You can finish the rest of the computation. Right. So here, what is given is that um, so A and X are matrices. There's 5 cross 4 and 4 cross 1 matrices. Uh, so you can think of A as being a map from um, from R4 from R4 to R5. And X is basically a 4x1 matrix. So you can just think of X as being an element of R4. Okay. So now it is given to us that AX equal to 0 if and only if X equal to 0. Well, what does this mean? It means that the nullity of A is just equal to 0. Okay. So A is a full rank matrix. So A must be a rank 4 matrix. So the rank of a matrix can be at most the minimum of the dimensions of the domain and the target space. So if we had a map A from U to V, then the rank of A is always upper bounded by the minimum of the dimension of U and the dimension of V. Okay. So in this case, X. So when this less than or equal to is an equal to, we say that A is a full rank matrix. So here A is a full rank matrix. It is a matrix of rank 4. Okay. Um, okay, let me see. Let's look at this problem. Okay, so here the linear map is just the derivative operation. So now the question is, then the matrix representation of T denoted by A is an idempotent matrix. You have to choose which of them is the correct. So, so what is an idempotent matrix? So you say that the operation is idempotent if T square is equal to T. Okay. Um, Now, of course, this is not necessarily true because if you take the second derivative, then this is not equal to P dash X in general. Okay. Um, so idempotence is not necessarily correct. But what we do know is that uh, because the polynomials have degree at most three, um, if you keep on taking the derivative operation, then after a certain point, uh, it's going to be equal to zero, right? So in particular, um, if you take um, if you take the operation four times, so let's say uh, P k denote the kth derivative of x. Kth. So then you notice that P4 is identically equal to zero. Okay, which means that if you perform this operation four times, it is going to be equal to zero. So you basically what you get is that t raised to the power 4 is equal to 0. So it is a nilpotent matrix of index 4. Okay, so we say that a linear map is a nilpotent map if there exists some k such that t to the power k is equal to 0, then t is nilpotent. Okay, so I hope this was clear. Also look at this problem. Just give me one moment. Um, okay, I'll just be back in like few minutes. Okay. Right. So, right, we're given matrices AB plus B square is equal to C, and it's given that C is a non-singular matrix. So, let us just recall a quick fact. So, if you have if you take the product uh, of two matrices A and B, and if you ask what is the rank of uh, of A and B of this product AB, so uh, the rank of the product AB is always less than or equal to the minimum of the rank of A, comma the rank of B. Okay. Now here it is given that C is non-singular. So non-singular means that it's full rank. So that means that rank of C is equal to N. So now you have AB plus B squared is equal to C, which means that A plus B times B is equal to C. Okay. So it therefore follows that the rank of B must be equal to N, and the rank of A plus B should also be equal to N. Okay. So B must be non-singular. A plus B must be non-singular. Okay. So B and C are obviously correct. Now, the question is um, if B is non-singular, and also A plus B, so both A plus B and B are non-singular, then is it true that A is also non-singular? So we will want to verify this option A. Then is A also necessarily non-singular? And the answer is false. You can easily check that that A might be a singular matrix, which when added to B, basically gives a matrix of which is uh, non-singular. Okay. So an example could be something like this. So you could take uh, B to be the identity matrix. Okay. And you could take um, A to be a matrix of this form. 1, 1, then all zeros, and all other columns are equal to 0. Okay. Or maybe not this. Let's say you write this as equal to 0, 1, this, and everything else is just 0. This is a big block of 0. Okay. Now, if you add A plus IN, you will notice that this is non-singular. But of course, A is a singular matrix. So B and C are correct. Okay, I think I don't have any more problems to discuss today. Um, yeah, I'll wait for a few more minutes. If you have anything to ask me, you can ask me. I won't have any other problems to discuss today. Okay, I guess there are no more questions. Um, so let's let's